Hi, my name is Julia. I'm an AI researcher at Circle. Today I wanted to talk about something that has been a hot topic for years now, whether one day we will be able to develop general artificial intelligence. With the development of computer programming, this question has found its resolution in the technical means. However, even after more than 60 years of trying to recreate our own brain, we're still where we were. Artificial intelligence that is as smart or even smarter than humans has been a subject for ardent debate. Not only how to create what's called general artificial intelligence, but also whether it's in principle possible if we don't really know how our own brain works. This is where the philosophy of AI steps into the game. In this video, we'll talk about what general intelligence is and what approaches to its development exist today. Why do people keep asking if one day we will be able to create AI when it is clearly used to recommend your content on social media, help find information on Google, or even evaluate your health? The thing is, there are different types of AI. So let's start from narrow or weak AI. Weak or narrow AI is good at performing a particular task, but it will not pass for humans in any other fields outside of its own. You have probably heard of Deep Blue, the first computer to defeat a human in chess. Not just any human, Garry Kasparov in 1996. Deep Blue could generate and evaluate about 200 million chess positions per second. To be honest, some were not ready to call it AI, while others claimed that it was one of the earliest examples of weak artificial intelligence. Nowadays, narrow artificial intelligence is widely used in science, business, and healthcare. Consequently, there is strong artificial intelligence, or general AI, that seeks to create artificial persons, machines that have all the mental powers we have and can use their skills across different fields without being programmed to perform them. With the appearance of general or strong AI, on the other hand, machines become more like humans. They make their own decisions, learn without any human input. Not only are they competent in solving logical tasks, but they can also have emotions. The question is how to build a living machine. You can program the machine to produce some emotional, verbal reactions in response to stimuli. For example, chatbots and virtual assistants are already quite good at maintaining a conversation. Also, the experiments on teaching robots to read human emotions are already in action, but reproducing emotional reaction doesn't make the machine truly emotional, does it? While to create narrow AI, you almost entirely rely on programming and algorithms, in order to create general AI, artificial persons, you have to go beyond the computer science field. In order to model your own brain, we have to use knowledge of cognitive science, psychology, semiotics, and philosophy. AI researchers have to discover new ways on how to model own consciousness and recreate it with technical means. So, do philosophers have any ideas about how we could design general artificial intelligence? Well, the truth is that not everybody agrees that it's possible. Probably the most famous person who believes that a computer executing cannot have a mind of consciousness of its own, regardless of how smart it looks, was John Searle in his paper Minds, Brains and Programs, published in Behavioral and Brain Sciences in 1980. He proposed a thought experiment called the Chinese Room. So he says that artificial intelligence research has succeeded in constructing a computer that behaves as if it understands Chinese. It takes some input in Chinese, produces some output in Chinese. Suppose it does it well and convinces a human Chinese speaker that the program is itself a Chinese speaker. However, does it mean that the machine literally understands Chinese? Or is it merely simulating the ability to understand Chinese? If it does, then we created strong AI, but if it just simulates, then it is still weak AI. Searle then asks the reader to imagine that he, the author, is in a closed room and has a book with an English instruction and everything he needs to pass the message. So Searle could receive Chinese characters through a slot on the door, process them according to the instructions that he has, and then produce some Chinese output without understanding it. If the computer had passed the Turing test this way, then Searle also did that, just running the program manually. Searle argues that without understanding, we cannot describe what the machine is doing as thinking, and since it does not think, it does not have a mind in anything like the normal sense of the word. Therefore, he concludes that there is no strong AI. So he understood strong AI as computers that have minds in the same meaning that humans have minds. He thought that computational models of consciousness are not sufficient by themselves for consciousness. The computational model for consciousness stands for the consciousness in the same way the computational model of anything stands to the domain being modeled. Nobody supposes that the computational model of rainstorms in London, he says, will leave us all wet. But they make the mistake of supposing that the computational model of consciousness is somehow conscious. It's the same mistake in both cases. You can read more about it in his work Consciousness and Language. It is true that the experiment afterwards has been found to be flawed, because if you think about it, even the person in the Chinese room does not understand Chinese, but the whole system does. But now we have to talk about the Turing experiment that I mentioned. So we said that the Chinese room experiment implements the Turing test, right, to estimate whether the system is truly conscious or not. But what is this test? According to Turing, to understand whether or not the machines behave like a real human, you need to conduct an experiment. If a person is unable to distinguish between a real person and a computer, then we have succeeded with the creation of general artificial intelligence. He proposed a test that the computer would pass if the human experimenter, having asked certain questions in writing, was unable to determine whether the written answers were from a real human or a machine. That looked almost impossible in Turing's times, which were 1950s, but even today building a chatbot that is able to maintain a natural conversation is still not an easy task and requires a lot of resources. Today we can create a model that is able to successfully resolve a task, think of Siri or Alexa for example, because they were trained in enormous amounts of data. And sometimes during conversation you might mistake chatbot for a real human agent, even though it's usually rare. However, does it mean that Siri or Alexa are examples of general artificial intelligence? Not really, because they operate only within a limited range of tasks and sometimes make very stupid mistakes, such as even a 5-year-old wouldn't make. So it means that we still need to search for other ways to approach general artificial intelligence. An approach that has attracted scientists for many years and is still prevalent in the research consists in first understanding how our own brain works using self-observation and experiment, and second try to simulate it. For example, neural networks that enable deep learning, the closest to AI that we have today, try to recreate the structure of a human brain consisting of neurons and neural connections. Similarly, we can observe ourselves, create some theory of thinking, and then try to represent it in formulas and programs. If we see that given the same inputs and outputs, human and machine produce the same result or show similar behavior, we can say that the program works exactly like the human brain. Cognitive science, psychology, and social science help us to come up with cognitive theories that artificial intelligence can be based upon. Experimental studies in this case add additional importance to the validity of such an approach. In fact, this approach to the development of artificial general intelligence has helped us to make significant contributions to the field of computer vision, image processing, and recognition, and everything that relates to such as face recognition or self-driving cars. However, the problem is that with this approach, our knowledge of our own cognitive abilities is still very limited. While it's relatively easy to program a car that will drive itself in a certain region, it's much more difficult to help it operate in difficult tasks and unexpected situations, such as if the brakes broke off and the passenger inside and the child is outside, and what should you do? Who should you choose? Humans make such decisions in seconds, and it's not always clear based on what. Another problem with the experimental approach is that human consciousness is too fluid to be reproducible. Different people might arrive at the same conclusion using different ways, and the next day might act completely differently. Do we really want our AI models to act the same way? Are we able to encode this variety and variability? These are the questions that we still have to answer. There is another approach that seems quite promising. We already said that artificial general intelligence should act as an artificial persona or agent that is different from a regular computer program, since they have an ability to function somewhat autonomously, perceive the environment, and act based on the observations. A lot of people actually do that. This theory allows us to move forward from rule-based thinking and put an emphasis on thinking rationally, adequate to the environment. For example, sometimes it's impossible to choose the correct action, but life still requires you to do something. For example, if a dog is trying to bite your arm, you just need to get away without a careful consideration of all consequences and circumstances. That means that for the system to be truly intelligent, it needs to accumulate and represent knowledge and reason based on it. This alone would provide for it developing acceptable solutions in many different situations. The agent must strive to learn not only how to solve a task, but to understand the world better as a whole so that it could develop effective strategies for acting in this world based on the erudition. It needs to be able to observe the environment, for example, through visual and auditory perception. Agent-oriented approach best approximates human behavior that is well adapted not only to one particular environment and is the product of a complex and largely unexplored evolutionary process. This approach simplifies the task of creating a rational agent and provides a suitable basis for describing much of the theoretical material in this area. There are other theories and ideas that try to reason what artificial general intelligence is and really consists of. Moreover, some experts say that none of the existing theories are good enough and we still need a new theory of intelligence in the future to create general artificial intelligence. The reason why they say that is because our progress in the area is very slow. One reason is because we face computational difficulties. Only a few companies in the world allow training models that show really impressive results. Another reason is a conceptual problem that I have mentioned. We don't even know if our understanding of intelligence is correct and enough to try to recreate it. Since the discovery of neural networks, researchers haven't found anything as significant that could move the industry forward. Moreover, in order to progress in artificial intelligence development, researchers must have not only profound knowledge of programming and computer science, but also cognitive science, neurophysiology, and that is obviously hard to achieve. Today we have discussed different approaches to developing general artificial intelligence. If you liked this video, please let us know and don't forget to subscribe.